For part D, trapezoids, you have two options. You can either go through area formula for trapezoids, or you can go through and find the average of left and right rectangles. So see if I can do both, and you can decide which one you prefer. Make sure that you remember when you find the average of two numbers, you're adding them and dividing by two. You're not subtracting and dividing by two, right? Okay. Any questions with page 1 or page 29? Okay, next page. We're moving into limit definition of area. So this is where we have to go through the whole limit formula, width formula, summation. And I'll put those up in a second where you can reference them, and I'll also be provided for you on the quiz. Does anybody still need to look at page 29? Okay, so the first thing that we can start off doing is building our width. Remember, we have to hold on to our end value. If we're doing exact area, we're not going to have a set number of rectangles. We're going to push that n out to infinity after we collect all the ends. So start off with your width. Your A is your left endpoint. Your B is your right endpoint. Okay, next step is to put into your area definition. A plus width times I. What's our A value? -1. I said F here, but really we're just putting to that g of x functions. So our g of x function is 6 minus x squared. So in order to get this out of function notation, we have to do some substitution, right? So everything that we see here is going to go into the x of that function. Okay, so now this is a standalone problem. We're just going to be expanding this out, cleaning this up. And once everything is resolved, then we can rely on our summation formulas to eventually get it to the point where we can compare degrees and evaluate our limit.
Isn't it something negative 6 and 9?
You mean over here?
Yes,
It was,
I'll be changing.
yeah, but then I distribute that negative through. Okay, any questions with 5? All right, next up, number 6 is going to be a power rule problem. So we put integral around our expression, and let's get every term set up and ready for power rule. So remember the conditions for power rule: no variable in the denominator, no radicals, and no parentheses. All those things have to be in place before we apply power rule. Let's just start off with using the integral notation to indicate what we want to do. I'm going to do a little bit of cleanup along the way as I set it up. So if we want to do power rule, we want to make sure every term is ready. The first term is ready to go. I want to just copy it down if it's ready.
How do we know to add the dx at the end?
Oh, whenever you see integral, they're always come in pairs. If there's an integral notation, there's a dx at the end as well.
At the end of the last term?
The last term, right.
Mr. User, help session.
Yeah, Thursday morning. How do I get this third term ready for power rule? Does a 2 stay in the bottom though?
Yes.
Yes. Okay. So 2 stays. It's the x that needs to move. So and same thing with the last term, right? 1/3 x to the -3. Okay. So if we look, every term is nice and ready for power rule. Coefficient is going to stay, but it's going to be the variable that gets impacted by power rule. What happens to pi? Good, pi x. Pi is a number, so any number is going to rise to a degree 1 variable. So if it was 3, it'll become 3x. If it's pi, it becomes pi x. I'm going to bleed into the next problem here. The next problem is not going to use a lot of space because you're just going to find the integral. So I'm going to just do the cleanup here. 5 cancels out. Dividing by 1/2 is the same thing as multiplying by 2. Three and -2 is -6. I'm going to drag the x squared below. For number 7, we're asked to find the antiderivative. Remember, we're going backwards from derivative rules. So the hope is that we can just write out our derivative rules and just read our derivative rules from right to left. So what's cosine going to turn into? sine, right? So the negative is not going to go away. So it's just going to be sine is going to turn into negative cosine. And cosec and cotangent is going to turn into positive, because there's a negative that's outside the rule and there's a negative inside the rule. Okay, number 8, find the most general expression for f of x if f double prime is equal to. So how do we get from f double prime up to f of x? Take the integral antiderivative how many times? So I'm just going to use the integral notation to spell out what I want to do before I actually do it. Now I want to resolve the notations, and now we can go through a power rule for each. Plus what? It says find the general expression, so we're not going to solve for any of the c's here. We're just going to hold on to them. Let me clean f prime up. Okay, so to find f of x, again, integral to indicate what I want to do. Power rule again. What happens to the c here at the end? Cx. But this is going to also produce its own what? C sub 2. Or plus k, whatever. It's another common thing you can do. Or I'm going to bleed into number 9. Number 9 won't take a lot of space here, so let me clean up f of x here. For number 9, we're asked to find a specific expression, and we want to find the integral of g of x. So there's my g of x here. So I'm just going to set up my problem here. I'm going to take the integral of that 3x squared minus 4x. We set up the notation before I actually do my calculus process. Okay, so we're just a power rule away. A plus c is going to show up, and they're going to give us an order pair for us to use and solve for c and update our f of x. So -1 goes in for x, 2 goes in for y, or f of x, and then we solve for c. Okay, there's also going to be an extended power rule problem that's going to be on the quiz. And I have it on, we'll do one problem each day leading up to the quiz. So on page 37. So you'll see a problem like this where you're asked to find the integral. It's going to be an extended power rule problem. We have to split up into individual fractions, get every term ready. So let's do one of these now. So as I work through it, you can also check your progress with page 38. So remember, there are three conditions for power rule. No radical in the denominator, no variable in the, sorry, no radical. That's number one. No variable in the denominator, and no parentheses. So I'm going to put integral notation around it, and then along the way, I'm going to start splitting up because my numerator is already mostly ready to go, but I do have to kind of start splitting up into individual fractions here.
For some they're over 2 and the other ones are over 2/3.
Oh, sorry. My bad. Yeah, they all should be 2/3. I copied wrong. Thanks. One mistake that I've seen in the past, and this connects with last semester too, where we had similar starting point before we did Power Rule, is this is not ready for Power Rule. Some students will start doing Power Rule each individual term, but these are not, these are still connected. We have to get it down to 1x before. And also, last semester, students would take this and make the derivative 0, and they saw, oh, that's a constant. So that constant doesn't go away because it's not really a constant. It's still connected to this term here. So we're not ready to apply anything with calculus until all these x's come up and all of these x's merge into 1x. The way we do that is we subtract the exponents. And as we subtract the exponents, the fraction is going to stay. Okay, the 2 is going to stay. It's just the x that has to come up. So 3 minus 2/3, think of it as 9/3 minus 2/3. Six over 3 minus 2/3. You can also use your calculator. The 2's cancel out. 3/6 minus 4/6. So this is where we need to be before we apply Power Rule. Notice there's no more x's connected to each other, and all the x's have been cleaned up. No more parentheses, no more radicals, no more denominator variables. Okay, so now our next step, apply Power Rule, add 1 to the exponent divided by the new exponent. So the 3/2 is going to just hang out in front. The 7/3 is what's getting impacted. 10/3 over 10/3. 4/3 becomes 7/3 over 7/3. Negative 1/6, we add 1 plus 6 over 6, we get 5/6 over 5/6. Negative 2/3, 1/3 over 1/3. And then our final step is cleanup. Let's bring all the fractional values up. So the way we divide a fraction is multiplied by the reciprocal. So multiply this by 3/10, this by 3/7, this by 6/5, this by 3/1.
What happens to dx?
Remember, whenever we do, when we start off before we do Power Rule, the notations will stay. But as soon as we do Power Rule, those notations drop out in place of it. We have to Okay, let's begin worksheet 2, page 31. So now we have an idea what the quiz format would be like. We're just going to go through and just start continuing getting more reps under our belt. So page 31. Okay, so we're not going to use summation formulas here. There's only a few terms to add. So start off with 2 and then start replacing your I values with numerical values that increase by 1. And then you're using your calculator to get that sum. Okay, page 31, worksheet 2. Any questions with 1? Oh, before I forget, I'm gonna have you guys stay with me for advisement today because of um, all the things we're gonna do today for yeah, we have a bunch of drills today, so I'm gonna have you guys stay here. All right, so number 2, try to get it into a summation notation formula here. And we start off by putting down the parts that we see as not changing. What pieces are staying the same throughout? What else? Five minus, yeah, radical, right? So we know whatever is not changing, you want to just go ahead and put those down. And you know that the parts that are changing is going to be where you have variable I and be involved because that's what's causing every term to change. So we want to start, you want to find a formula where I equals 1 will produce this term, You want to plug 2 in to get that. You want to be able to plug 3 in to get this, and you want to plug 4 in to get that last one. So think about a couple of options here. Maybe it's involving multiplying by a constant. Maybe it's involving raising that variable to a power, or it could be involving an exponential function, a number raised to a variable. So a little bit of trial and error, a little bit of exploring what could work. What could go inside the square root? The denominator has a different pattern here. Squared, okay. And let's test it out, right? Plug 1 in, we get 2 over 1 squared, that works. Plug 2 in, 4 over 2 squared, that works. Plug 3 in, 6 over 3 squared, which is 9, that works. Plug 4 in, 8 over 16. And my upper bound is 4. That's the final last I value that will give me the last term. Okay, number 3, start off with width equals d minus a over n. And then populate your number line so that you can see your intervals. Width ends up being 7 minus 3 over 3, which is 4/3. So starting with the left endpoint, keep adding 4/3 until you get to your final endpoint, which is 21 over 3, which is the same thing as 7. It's asking for 3 left-handed rectangles, so there's no need to find midpoint. We just rely on these original interval values that we found. And then do width times height for your 3 rectangles. I would start in function notation, and then you can plug the fractional values into your calculator. Okay, so first rectangle, we want to use f of 3 as the height. For the second rectangle, we want to use f of 13/3. Third rectangle, we're going to use f of 17/3 because we want left endpoint for each. Okay, number 4, table of values. You're picking off your width and height. Remember, your width comes from subtracting X values in the first row. Your height comes from just pulling the appropriate Y value from the second row. For part C, for trapezoids, again, you have 2 options. Either memorize the area formula for trapezoid, 1/2 width, height 1 plus height 2, or find left rectangle sum, find right rectangle sum, and then average between those 2 values. Let's see if we can spend 5 minutes getting started with number 5. Back to limit definition. And your homework is just to finish page 29, 30, and 31. Basically, we've done everything in class. Just have to finish this problem 5. So I'll send out a reminder, and I'll also send a link to this page if you're not quite finished yet.
Good morning, Milton students, visitors, faculty, and staff. Please stand for the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America, and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Please pause for a moment of quiet reflection.